Okay, we're going to take a closer look at input-output tables and find out how they're used and what they actually represent. So what we've learned so far already is that an input in this case is going to be n. That is our unknown, and what we're saying is that we're going to take n and we're going to give it different set of values, and we're going to input that into our algebraic expression. Now in this case, our algebraic expression here is going to be 3n minus 1. Okay, so that's going to be our algebraic expression. So what we're going to do is we're going to take a bunch of different input numbers here. So let's take 0, 1, 2, and 3. And what we're going to do is we are going to input those numbers into this algebraic expression to develop an algebraic equation, something that we can actually work with. So what we got here is we're going to start with the first one. So it's 3 times 0 minus 1 is going to actually equal negative 1. And then here we've got 3 times 1 minus 1 is going to equal 2. And then here we've got 3 times 2 minus 1 is going to equal 5. And then here we got 3 times 3 minus 1 is going to equal 8. Right? That is a very simple way that we have conducted a simple input-output table based on n, these being our input numbers, into our algebraic expression here to produce our output, which is these answers here. Now let's take a look at how input-output tables, how we can actually figure out algebraic expressions based on information already given to us by an input-output table. Let's take a look at how this input-output table works out here. As we can see, we have our input numbers here along this side, and we've clearly got them labeled here 1, 2, 3. Those are going to be our inputs. Those are going to be what we're going to input into the algebraic expression. Problem: we don't know what that algebraic expression is yet. Whoops. We don't know what that algebraic expression is yet. Okay. But we are going to find out. So what we have to do is we actually have to start off by looking for patterns in the output. What we've been given is we've been given the output, which basically says when we input n as 1, when n is inputted as 1, the output answer is 5. So that's how what we're going to use to figure out what our algebraic expression is. So the first thing that we need to do is we need to take a look at the pattern that's going on here. So what we can see is when n is 1, we know the output is 5. But when n is 2, the output is 8. And what we can see here is that there is a difference, and that difference is plus 3. And when n is 3, we can see that our output is 11. And once again, that it increases by 3. And what we understand about multiples is that if this is going up by 3 each time, this must be a multiple of 3, because this is basically like skip counting. 3, 6, 9, 12. And if you think of that, that's 3 times 1, 3 times 2, 3 times 3, and 3 times 4. So there's clearly one of the statements is a multiple of 3. So we know that we've already got 3 times a number. So we already know that we've got 3n. And we know that right here, when n is 1, that it has to equal 5. So let's take that one for starters. 3n has to equal 5. So let's say, well, let's plug in 3 times 1. And the question is, does that equal 5? Well, clearly it doesn't, because 3 times 1 is 3, and 3 does not equal 5. So the way that we got to figure this out is we say, well, if we've already got 3, how can we actually make this statement true? How can we make this side equal to this side? Well, all we have to do in order to make this a true statement is say, well, let's just add 2 more in there. So in actuality, what ends up happening is we can say 3n plus 2 equals 5. So let's write that in for our output here. 3n plus 2 is our algebraic expression. Well, let's test it out to see if it works for our other output numbers. All right. Well, let's take, hang on, we'll just clean this board up a bit. All right. Let's try out our algebraic expression that we just came up with, and we'll try it on 2. Okay, so let's input 2 into our algebraic expression here. So we have 3 times 2 plus 2 has to equal 8. Well, based on our order of operations, we know we got to multiply first. So 3 times 2 is going to be 6 plus 2 equals 8. And we know that 6 plus 2 in fact equals 8, so therefore our algebraic expression is true no matter what n we input. If we inputted 3, the output would end up becoming 11. Let's take a look at one more example. All right, let's take a look at another input-output table here and see what we can come up with. All right, so we don't know what our expression is yet. It's an unknown right now. But what we do know is we already know what the input numbers are when we put n into the algebraic expression, what our output is going to be. So let's take a look at the one I always like to start with is the number 1. I always find that one's a nice, easy one to start with. All right, so let's take a look at our output numbers. And let's see what kind of a pattern emerges here. Well, we can say that the difference between 3 and 7 is an increase of 4. It goes up by 4. And 7 to 11, it goes up by 4. And 11 to 15, it goes up by 4. And so now it looks like we're skip counting here by 4s. So we automatically know that n is a multiple of 4. So we can say that 4 times a number has to equal our output. All right, so let's start with number 1 because I always like to start with a small number first, and 1 is always a good one. So we know that when n is 1, so when we put the number 1 in for n, the final answer is going to be 3. So let's do that. 4 times 1 has to equal 3. Well, 4 times 1 is 4. And that doesn't equal 3, but I have to ask myself, how can I possibly make this statement a true statement? Well, all I have to do in order to make this actually equal 3 is to take away 1. So if I go 4 minus 1 equals 3. So if I say 4n minus 1 equals 3, this is also a true statement because when n is 1, it does equal 3. Well, let's try it out with a couple of the other ones. Let's see. So let's put it in here. 4n minus 1 as our algebraic expression. Let's try it out. Okay, let's try. Let's take another number here. Let's take the number 3. Okay, and we're going to say, you know what? We're going to input this number 3 into our output and see if it or into our algebraic expression and see if our output is in fact 11. So what we're hoping to say is that when we take 4 and we multiply it by 3 and we subtract 1, it's going to give us an answer of 11. All right, well, 4 times 3 is 12, and 12 minus 1 is clearly 11, so this checks out. So it doesn't matter which input we put in to our algebraic expression, it's always going to work. All right, let's look at a little bit of a different example here to really wrap our head around the process that we go into. Now, the first thing we have to do is we have to look for our pattern to find out if there is any multiples that are involved here. So let's take a look at this one here. We've got our input here, and when the input is n is 1, our output is 9. When our input is 2, our output is 8. And as you can see, we're starting to see a pattern emerge here. Okay, so let's take a look first at our pattern. Okay, and as you can see, it is dropping by 1 each time. So we know that there's no multiple that's in here, but it is going down by 1 each time. And so we know that we are subtracting a number here. So for example, we know that we take some unknown number and we take a number and we subtract n, and it's going to equal our answer. So we're subtracting n here. Now, when n is 1, our output is 9. So the question is what number do we put in here to make this statement true? All right, well, in that case, it's going to be 10. So if we were to say 10 minus a number is our algebraic expression, that would in fact be a true algebraic expression for this input-output table. Let's take a look at, let's try a couple others to see if that is in fact true. All right, well, let's try 4. All right, so let's say 10 minus a number has to equal 6. All right, and let's say that n is in fact 4. So what we're going to do is say 10 minus 4 equals 6. That is a true statement. All right, let's take a look at another example where we're using this subtraction. Okay, what we can see here is that this is another bit of a different pattern, but we can see that each time the number drops by a multiple of 2, because it drops by 2 each time, but it's a multiple of 2. So we know that we are actually in fact subtracting 2 times a number here. So that's how we're going to get started off, is by saying it's subtracting 2 times a number. So let's take a look if we were to input 1 into this equation. So what we're going to say is when n is 1, our output is going to end up being 14. So let's write in 14 here, and we're going to say when we take away 2 times 1, it is going to equal 14. Well, we get ourselves a little bit of a problem here because we don't know what exactly it is we need to take away. So 2 times 1 is obviously 2, and that's going to equal 14. So we have to say, well, this statement so far is not true. What could we do to make this statement true? And that is simply put in 16. So what we can say is that our expression should be 16 minus 2n. So let's try that, 16 minus 2n, and we're going to try it with a couple of numbers here and see if it works out for us. All right, let's start by selecting the number 3. So we're going to take our expression here, which is 16 minus 2n, and we're going to plug in the number 3 for n and see if it comes out to 10. All right, fair enough. Let's take 16. We're going to subtract 2 times a number, and we're going to see if that, in fact, equals 2 times a number, and we're going to see if that, in fact, equals 10. All right, well, 2n is, n is going to be 3, so it's going to be 16 minus 2 times 3, and that's going to equal 10. Now remember, order of operations says we always have to do division and multiplication before we do addition and subtraction. So therefore, we need to solve this problem here before we subtract it from 16. So it'll be 16 minus 6, and in fact 16 minus 6 does equal 10. So we know that our algebraic expression here, 16 minus 2n, is a good one.